In this video, we are going to learn about RAID. RAID is a redundant array of independent disks. Because of its property, it is also called as inexpensive disks. Actually, there are 7 basic levels, out of which 6 levels are in common use. These all levels are in not a hierarchy. They are independent of each other. So whenever we want to recover the data using RAID methodology, any of the RAID level can be implemented. That is the reason we say them as independent levels. So this set of physical disk drives will be viewed by the OS as a single logical drive. That is, even though we are having separate disks physically, the OS will be looking them as a single drive. The data are distributed across the physical drives of an array. Whatever we want to store in the system, they will be stored in different disk drives. So redundant disk capacity, in order to store some redundant data, we require some extra disks. This redundant data will be helping us to recover the data when there is a damage or loss of data. So this RAID actually improves the access time and also improve reliability. The first very basic level is RAID level 0. Actually, this is not considered as one of the RAID levels because no redundancy will be incorporated in this. One single logical disk, what we are seeing from strip 0 to strip 15, will be divided into 4 physical disks in a round robin method. So this distribution of data from logical disk into physical disks will be carried out by a management software. So the round robin method means first strip 0 goes to physical disk 0, strip 1 goes to physical disk 1, 2 goes to disk 2, strip 3 goes to disk 3, and now again strip 4 goes to physical disk 0, strip 5 goes to disk 1. Like this it continues until all the strips are mapped to one or the other physical disks. The next one is a RAID level 1. In the RAID level 1, redundancy will be the high level. We can say highest level, because whatever the data disks we are having here will be replicated as it is. So this is called as mirroring method. So whenever we want to read a data, it can be read from either of the disk, either from the original disk or the duplicate disks we can read the data. So this will be helping us for shorter queuing, and also rotational delays will be very less. At the same time, seek time will be very less in the case of RAID level 1. The mirroring method, that is RAID level 1, will be used in the case of applications where we require more availability and transaction time should be less, but storage is not a problem. That is, cost efficiency is not a problem. It can be more cost also. RAID request requires both disks to be updated, but this can be done in parallel. So when you are writing or updating a particular strip, let us say strip 8, it has to be done in both the disks. So, but because we are doing that in parallel, it doesn't matter. Reading can be done from either of the disks. Suppose if I want to read strip 4 and strip 8, it can be done in parallel even though the strip 4 and strip 8 are in the same disk actually. The disadvantage is the cost, and it requires twice the disk space because all the data we are duplicating it. So the RAID level 1 improves the read request actually when both the disk members participate. That is, as I already specified, if these both are participating or these both are participating in the disk reading, then it will be more advantageous. This is the very basic advantage when compared to all the other RAID levels in the case of RAID level 1. Now coming to the RAID level 2, when we see the RAID level 1, we can see that the requirement of space is more number of disks are required. So in order to reduce that cost, bit level stripping is introduced and Hamming code is introduced in the place of mirroring method. So the redundant data is maintained using Hamming code method. So if you see here, B0, B1, B2, B3 are the data disks, F0B, F1B, F2B are the redundant disks. So whatever the bit we are having in a particular position I of B0, B1, B2, B3, the Hamming code will be found, that is check bits of the Hamming code will be found and put into F0B, F1B and F2B. Bit level stripping is nothing but if we are having a 4-bit data, first bit will go to B0, second bit to B1, third bit to B2, fourth bit to B3. This is called bit level stripping. And easily we can rectify the data whenever a particular disk is failed. So when a particular disk B1, let us say it is failed, then in that case this can be recovered from B0, B2, B3, F0B, F1B or F2B. But because in this case, in the case of RAID level 2, we need multiple redundant disks. That is, all the disks we need to identify whether a particular disk is failed or not. But we need only one disk in order to recover the lost information. How is this? We'll see later. The next one is the RAID level 3. Next, RAID level 3. Even in RAID level 3, bit level stripping only is followed. As we already told, first bit will go to disk 0, second bit to disk 1, third bit to disk 3, so on. And now instead of using Hamming code, we are using parity to maintain the redundant data. What happens here is the number of disks we require in order to store Hamming code will be more when compared to store the parity data. When we are calculating the parity and maintaining it in a disk, we require only one extra disk when compared to the data disks. In comparison with the Hamming code, Hamming code will be requiring log number of data disks in order to maintain the Hamming code redundant data. Here what happens when we are performing a read request or write request is all the data disks are required to access when you are supposed to read a particular data. When you are writing a data, then all the disks including the parity disk need to be accessed. So only one request can be serviced at a time. Now RAID level 4. In the case of RAID level 3, we can see we are using bit level stripping. But in the case of RAID level 4, we use block level stripping. Block will be having one or more words actually. So what happens here, let us consider that each block is having one word. In the case of bit level stripping, when you are considering one word, it will be one bit will go here and another bit, another bit, another bit here. But in the case of block level stripping, if block is considered as one word, one complete word will come here, second word, third word, fourth word. Like this it will be coming. And parity will be calculated using all the blocks, block 0, block 1, block 2, block 3 and store the data here. Like this, the parity will be calculated in the case of RAID level 4. Here also only one extra disk will be required in order to maintain the redundant data. One advantage in the case of RAID level 4 is if read request is smaller than the stripping unit, then we can access only a single data disk. But if you see in the case of RAID level 3, we have to access all the data disks in the case of read request. But in the RAID level 4, there is a chance to access only a single disk or two disks it depends upon the data size, we are going to perform a read request. In the case of write request, we have to update the requested data block and also the parity block. In RAID level 4, in the case of write, suppose if it is a large write, that is we are going to write more amount of data, then it may require to access all the disks. In such a case, it is very easy. We can write the data in all the disks and at the same time we can update the parity disk also. But if it is the case of small write request, then actually it can be stored only in one of the data disks. But the parity is depending upon the other data disks also. So what happens in the case of small write request is we require 4 disk accesses. So one is to write the new data and the other 2 to read old data and also old parity for computing the new parity, and 1 to write a new parity. So because the parity is depending upon the existing data also, we are because the write is small request, that is small amount of data only we are writing. We are supposed to access the disk where we are writing the data and also the corresponding disk and the parity also, and at the same time we are going to update the parity also. So these all things will be considered as 4 disk accesses, and here we consider this as read, modify, write procedure. Now in the case of RAID level 5, a small difference when compared to the RAID level 4. In the case of RAID level 4, we are maintaining the parity in a separate disk actually, that is redundant data in a separate disk. But in the case of RAID level 5, it will be distributed among all the disks. So here there is no specific disk, what we call as redundant disk or a parity disk basically. So what happens here is block 0, block 1, block 2, block 3 parity will be calculated and stored in the last disk. And next block 4, block 5, block 6, 7. This parity will be calculated and stored in another disk. Like this, if you see here, the parity is stored in various blocks actually. So now RAID level 6. The number of disks that can be recovered is increased to 2 in the case of RAID level 6 when compared to the previous RAID levels, that is 2, 3, 4 and 5 actually. How is this possible is nothing but by increasing the number of redundant disk arrays. Instead of 1 disk array, we are increasing it to 2. So here instead of parity, what we have used in the case of RAID level 4 and 5, also 3, we are using 2 different parity calculations here in the case of RAID level 6. So 2 different parities normally what will be used in the case of RAID level 6 is general parity, even or odd parity can be maintained, and the other parity, that is other redundant code, is nothing but the Reed-Solomon code what will be followed actually. So here P we can say as parity and Q as Reed-Solomon code. So block 0, 1, 2, 3 parity will be calculated and stored here, Reed-Solomon calculated and stored here. So similarly it will be distributed as in the case of RAID level 5. It is a bit complicated one in order to rectify the data, and here we can see that there are 3 different kinds of loss of data. The first case, loss of 2 parity disks. Let us say that these 2 disks are lost. So what happens here, 2 parity bits are lost. Easily it can be recovered because data is already existing. And then Q here and block, that is 1 data block and 1 Reed-Solomon code lost and 2 data lost. So here what happens, we should be able to recover both the data blocks using 2 other data blocks and 2 parity blocks. And here using 1 parity and 3 blocks we are supposed to recover Q and block 7. And here it is only calculation is required actually. Thank you.